Okay, very well. Okay, now let's get back to our class. Continue to last subject. So today is September 19th, 2020. This is a third class in design of composite materials, or composites design. I prefer to say composites design. This slide is the last one. Again, the purpose of this micromechanics is that we calculate the stress amplification factors which relate between the micromechanics behavior and macro level behavior. So I like you to remember this slide. This is the summary of the micromechanics. So given material property is fiber resin, stiffness and strength, these are basically given inputs. And then we like to calculate homogenized stiffness. It's given as a C bar, which relates macro level strain and macro level stress. Well, what I meant by the macro is that we have a ply. Ply means one sheet, you can say sheet of the prepreg composite lamina, and let's consider as a one homogenized thin plate. Then the stresses applied to this material is called macro. So we like to know the relation between macro stress and macro strain. So in here we define the C bar. Again, it is called homogenized stiffness. Once we have a C bar, we can invert this C bar as S bar. It's a compliance. Once we have a compliance, we can calculate, homogenize the macro level stiffness or Young engineering constant, Young's modulus X, Y, and Poisson's ratio, and etc. Another one is that we can calculate stress amplification factors which relate between sigma bar. Again, sigma bar is the macro level, ply level stresses. And sigma is the local stresses at the micro level, which can be defined at any point, could be within matrix, or could be in fiber, or could be at the interface. And another one is the delta T is given as the macro level temperature increment, and the micro stresses sigma X can be related to this delta T. So A matrix is also can be defined relating delta T and sigma. So this one is the stress amplification factors. The main purpose of this stress amplification factor is to predict strengths of the UD composites, and which we will cover in this course. X and X prime, Y and Y prime S. In other words, X means fiber directional strength, and X prime is the compressive strength, and etc. So as a result, epsilon X and EY and etc. Those are macro level stiffness, and this is the macro level UD strength. So a given again is that I'm gonna rewrite. So given property will be a stiffness and strength of resin and fiber. Of course, you can think about the property at the interface. So these are given properties. Okay, these are given properties, and then this is the output property. I would say this is the stiffness of UD composites. So UD composite means that this homogenized the unidirectional composite. Okay, unidirectional composite means this one ply. So I repeatedly emphasize that sigma bar is the indicating the stresses at the macro level or ply level. This is a called ply. Just one ply has the one directional, unidirectional or unidirection. So ply usually means unidirectional composites. So please remember the role of the micromechanics. This is the again, first purpose is to calculate homogenized material property or ply level stiffness of a unidirectional composite is the that's one purpose, and the second purpose is to calculate the stiffness amplification factors. And using the stress amplification factors, we can calculate strengths of the uni composites. So basically, once we have fiber and resin, and through these micro models, we are able to get all the material properties we need in design of the composites. Okay, so this is the most important slide. And then, so what kind of a micro model we have? This is the basically micro mechanical models. Okay, this is the micro mechanical model or unicell, because this unicell represents one of the repeated modules in these macros, basically just one fiber and resin. But very importantly, there are repeated boundary conditions. Along this boundary, we have a repeated boundary condition. Repeated boundary conditions In other words, this unicell is not a separate model, which is just one of the repeated models. And there are very special boundary conditions which you can find even in Abacus and ANSYS. So please remember, when you have this unicell to calculate all kinds of material property, you need to apply proper repeated boundary condition along the boundaries. And one of the example is this model. Well, this again looks like a separated unicell, but this is not separate. This has the repeated boundary condition. Means that this is the one of the repeated models. I went through all these procedures, and to verify, this is the verify the unicell model you have. You will apply some boundary conditions, and you would apply same boundary condition, and you can see this one solution will be exactly same as that one. Exactly same, okay? This is the exactly same, and this solution will be repeatedly, it's just repeating. They are all same. When we apply some boundary conditions, those boundary condition is again repeated boundary conditions. It's not the free boundary condition, as I emphasize. I'm gonna okay. So those who like to study further and more deeply, understanding the micromechanics, please model this unicell, and then you apply a repeated boundary condition, and then you have multiple cells, and you apply the same boundary condition. This is the also same. Same repeated boundary condition, and then confirm that the values are exactly same as you can see here, and the maximum value are exactly same. So you can have many different types of unicell, as I explained before. You can have this a square model, and this is the hexagonal model, and sometimes a more simplified, the called OFM, octahedral fiber models, and analytical models, Shamis. There is the simplest one is the simple rural mixtures, and which you cover through as a homework. Okay, and there are several results, and as I explained last time, there were some experiment, the photoelastic technique. Then they apply some tension on the transverse directions, and this is the exactly same. This okay, so. We went through, and then last class, this was the last slide, which we covered last class. And again, how we calculate the engineering constant from this homogenized stiffness and C bar. And once we have a 6x6 homogenize the stiffness, how do we calculate the compliance? I mean, the engineering constant is just by inverting this stiffness matrix and get the compliance. and then you can, by definition, you can have the engineering constant like that. Well, some who may not be able to understand fully, you need to refer to the definition of stiffness. Now, today, I'd like to move to the next subject for this micromechanics. Well, as I emphasized, this is the cross section of the rear composite, and this is the fiber arrangement. So I would say let's well, this is the this represent the rear stacking and of several plies. So this cross-sectional view of continuous fiber composites, and well, this represents certain stacking of certain plies, several plies. I would say this is some fibers like that, and some fibers like that, and another one is this, and another one is like that. And this one represents, I would say here, okay, the fiber runs this way. And if we take a look at the cross section, there will be you can see the cross section of the fibers. And this is the picture of the real plies. And this has been modeled as we covered. One is a square, and you can, another one is hexagonal and diamond array, and so on. And the main reason we use this regular array is to introduce simpler models because otherwise it is going to be too complicated. But when we have these kind of models, we use the same fiber volume fraction. Okay, same fiber volume fractions means that total volume versus the volume of the fiber. That is the small VF. So usually VF is from 0.5 through sometimes 7. I would say 0.4 to 0.7, depending on the manufacturing process. Well, most standard one will be 0.6 for the regular RTM, resin transfer molding. And the, say, pultrusion will be pultrusion can reach like a 0.7, and RTM can be reached like 60%. Well, those who do not cannot understand fully these definitions, I highly recommend you to go through all the manufacturing process, and you need to get used to a terminology we are using. So anyhow, but as you can see, the real cross-section is not like regular like that. This real fiber is pretty much random. Random means that each fiber is not regularly arrayed. Their position is pretty much random. So random, but we have to have a same fiber volume fraction. So we can numerically generate a random fiber array, so that we like to get a more detailed, more realistic behavior or at the micro levels. So first we need to do how to generate these random fiber arrays. But again, the fiber volume fractions, VF have to be the same. Otherwise, it's totally different. Now, how to generate the random fibers? We can have established the algorithm so that given fiber volume fractions, we can generate fiber arrangement randomly, but reach the fiber volume fraction as specified. Since this is the randomly generate, so every time we generate, the pattern will be not the same. As you can see, this is the first time running, and this is the second time running, and this is the third time running. Each time you have a different fiber arrangement, because again, it is numerically randomly generate. But even though the distribution of fibers are different every time, but we have the same fiber volume fractions. Well, the algorithm has been developed that way. This is just a cross-sectional view, but if we take a look at the three-dimensional view, this is one of the models. And then again, the procedure is that once we have this kind of random generate, and then we can generate volumes of the fibers and volume of the resin, and you can generate the mesh. So again, the main purpose is that to study this random fiber is that how accurate these random fibers compared to real fibers. So this is the real fiber arrangement, and then we generate the mesh, and this is the artificially generated random fiber numerically, and then we apply the same load, and then see how these are related. Well, as a conclusion, as you can see here, the blue is the distribution of maximum normal stresses, and this red indicate the maximum shear stresses at the interface. Okay, every point, every fibers has the we can have a maximum normal stresses and maximum shear stresses, and we plot them, and we do the same thing using the real images, and we plot them for every fibers. And as you can see, the fiber stress ranges is quite same and normal stress and shear stresses. So the conclusion is that these artificially generated random fibers well represent the real fiber images. And so now we compare the stress distribution of the unit cell like that. And then this is the square model and hexagonal models. And then this is the random fiber model where we consider 120 fibers. And of course, these fiber, the stresses distribute from blue and to a red, and values are somewhat, I would say, distribute. And point is that these red, I mean, these two values are from this maximum that value, and this represent that value. So the maximum value are within these ranges. Well, this is the distribution of the von Mises strain, and this is a volumetric strain. Now, as a conclusion, we compare between the random fiber array and regular fiber array. This is the fiber volume fractions, and this is the fiber number. For this one is the result for the 60%, 0.6, and this is the maximum Tn, means at each fiber we have a maximum shear stresses. Okay, maximum shear stresses and normal stresses, but every fiber would have a shear stresses, maximum shear stresses, and we just plot them all. We pick the everything, and set 1 and set 2 means that the first time we generate is called set 1, and second time we generate another one is the set 2. So you can see how they are distributed. And here these three results are from a regular fiber array, and then this one, the results is from wide range of a fiber volume fraction from 0.1 to 0.7. And we plot the maximum, same as this value, maximum Tn, and as you can see how these values are changing depending on these three models. As you can see, three models would give us the, they are not exactly the same, they are different. So you can see different regular fiber arrays give us different values. But here what we like to do is that how this random fiber at fiber volume fraction 0.6 are compared with 60% of these models. And this, the value in red is the hexagonal. So hexagonal is about the middle ranges, and the blue one shows the somewhat, I mean the square represent about the maximum, and diamond array is the represent lower level, upper level, lower level, and some middle level. So from this result, you can see what this will help you to choose which regular fiber array. So square array giving us the most highest stress concentrate distributions, and hex is more likely average one. So if you use this scale, the stress is pretty much highly concentrated here. And whereas the hexa is the somewhat averaged, because the fiber distance between the fiber is the farther than scale models. So this is the good comparison between the regular and the random fibers. We cannot say which one is the best one, while they are certainly a choice of the designers. But if you have a want to be a more conservative, I recommend you to select scale one. The scale model is relatively simpler than others. Okay, that is the subject I like to cover. And this kind of a study can be applied to statistical distribution of the composite behavior. Let's say we have a strength of the open hole. Let's say this is the a open hole. Okay, open hole. Let's say open hole tension. This is the under tension, and then strength is not the could have some sensitivity on certain distributions like that, and this model can explain why we can have some distributed value. Well, there are many reasons for that, but at least the fiber arranging, I mean, microscopically, they are not exactly the same. So micro distributions would giving us different stress distribution, and also a matrix property could have some statistical distribution, and fiber property would have a statistical distribution and interface and so on. So this is the constituent material property have the distributions, statistical distribution, and this fiber arrangement has certain statistical distribution. So overall, the strengths of the UD property could have this kind of a strength statistical distribution. And then when you have an open hole, this is a laminar strength. This is the laminar strength. So in other words, this is the just a laminar ply strength. And then this laminar would giving us affect laminate strength and open hole strength. So this is the a relations, and we could have some distributions, and this is the shows the strength distributions. So well, this is not the exactly the same value, but this is a schematic drawing helping us the understand the composite statistical distributions. And same for is the same story. Now back to octagonal fiber models, OFM in short. This model will give us the analytical solutions and octagonal fiber shapes and fiber by fiber subregions. What it means is that for the given fiber volume fractions, this is the fiber volume fractions, and fiber is the model like that, and the regions are divided like that, and these are 5 by 5 subregion means that, okay, 1, 2, 3, 4, 5 regions, and also 1, 2, 3, 4, 5 regions. So totally 25 subregions, and where we can have only fiber. Sometimes we only have a resin area. And we apply, of course, the given property will be VF and stiffness and strength of fiber and resin. And then, of course, the stiffness of fiber and resin will give us constitutive relations and stress equilibrium and strain compatibility. This is always a 3 principles we need to follow. So we apply this governing equation to this model, and then we are able to get the Ply effective properties. C bar is the homogenized material property, and stress amplification factors, and M. And this is the subject I assigned you last week, and the derivation is basically stress equilibrium, strain compatibility, and stress-strain constitutions. And the derivation is relatively lengthy, but once we have these relations, everything is in terms of analytical form, analytically derived in terms of all these symbols or material property and fiber volume fraction we specified. So it's very convenient and easy to program rather than numerically calculating every time for the given material property and fiber volume fractions. And these results are compared, I would say, compared with other method like EX. This is a stiffness, okay, equivalent of stiffness. This is the shear and Poisson's ratio, and so on. These are material property, and these are FM and simple rural mixtures, and enhance the rural mixture. Okay, I need to double check, but this EROM means OFM result. Well, more. I'm sure you can find the result in the paper which I assigned, and this is the failure envelope. Okay, well, so far I repeat and reviewed again of the subject which we covered, and these are all the mainly on the micromechanics. This is the failure envelope. Okay, this is the failure envelope. in terms of sigma x and sigma y and sigma s, a three-dimensional space. And this envelope or volume represents the safe zone. So stresses are inside this envelope or volume. Then the material will not fail. But outside of this volume, the composite will fail. So that is the call of failure envelope. Okay, so as a continuation of a class, I'd like to cover more in the micromechanics. Well, I understand most of the subjects. Some subject is very new to you. I understand that. But again, this course is not just for the, these students have to go through, review, study from the internet. Nothing can be done easily. Nothing can be achieved easily. You have to go through internet and study in advance. So you need to spend some time and you need to study. And then if you have any questions, please feel free to share your questions through Katalog. So far, nobody expressed yourself, which is not good, not desirable. Feel free to share your questions. Don't be shy. The purpose of this class is not for me, is for you to learn a new subject. Well, learning new subject is starting from unknown concepts, unknown terminology. Please keep asking. If you don't ask, no answer will be given. Okay, this is the I will cover the micromechanics as a continuation of the subject we cover so far. So this is the micromechanics. Again, micromechanics is the two purpose. I mean, the homogenize and is the anisotropic stress-strain relations. This is the one ply. This is the one ply. And this is the, I would call laminate. Laminate. And one ply, just one of them, is called ply, or you can call lamina. This is the unidirectional composite or unidirectional ply, or this is the continuous fiber. This ply, of course, is consists of a continuous fiber. Continuous fiber, again, is the fiber is the not broken, is the continuous. It's not short, not long, but continuous. So these are fiber, and if we look at some of the regions, and then we magnify and pay attention to a coordinate. This is the x and y. This is the x and y, and this is a z, which usually indicated vertical axis. Okay, this is a z, and again, I just this local micro level indicate some portions of these cross sections. You may ask how many fibers we have here. Depending on the product, but I would say 20 to 40 fibers stacked through thickness. I just like to give you some figure so that you can have some idea. And the thickness of this unidirectional ply will be usually 0.125 millimeters. And diameter of this fiber, okay, this fiber diameter is about 7 micrometer in case of carbon, or sometimes 10 to 20 micrometer for the, this is the carbon and glass, and sometimes even bigger than 30 micrometer, or sometimes a little less than 7 micrometer. So you can imagine that this is the 125 micrometer, right? This is a 125 micrometer, and you can see how many fibers are stacked through z directions. Okay, so this, I hope this slide help you to visualize the how fibers are matrix arranged relatively. And well, I hope you not confused. This is the just a repeat, okay, repeat micromechanics problem statement. And the main purpose of this section is to get the go through micromechanics again using simpler models. As I assign you, I assign in the last homework, use a simple room mixtures. We like to calculate the stress amplification factors and homogenize the material properties. So this is nothing new, but this is just another repeat of the definitions. So fiber indicated by VF, and matrix is a VM. This is a volume fraction, and composites. And composite has a property of the stiffness and strength, and also thermal expansion coefficient is called alpha X and alpha Y, because we have a different thermal expansion coefficient of the thermal expansion, different CTE. And usually fiber volume fraction and fiber matrix of volume fraction equal to 1, but there can be some volume fraction of a void. This is the void. So if we neglect void, then the composite consists of only fiber and volume, but there will be some void. Void is 0 to, I would say, some can reach 2%. And micromechanics, we can have several different methods. FEM, we already went through. There could be a scale model, could be a hexagonal model, or could be a random. Of course, there was a diagonal models. And exact solution, not the exact solution, but I would say analytical solution, such as OFM. And then a rural mixture, which can be much simpler, and we can get the engineering level solutions. So this again shows the fiber arrangement from a photo taken showing the real cross sections. And this, some of the parts can be model. What do we call here? This model called scale. And this one is model called what? Hexagonal. So this is the, again, microscope of the composite materials. And this is the same slide we already covered in the scale model, subject to a transverse load. And this is the hexagonal model, subject to a transverse models. Okay, before we go through micromechanics in using this simpler rural mixture, we like to have 10 minutes break. Okay, let's have a 10-minute break. Okay, thank you. See you at 2:20. Okay, 2:20. We will continue to class. Okay. Let's continue the class. Would you turn on your video for a second? Okay, 원기, 경록, 지밍. Okay. Arcing glue. Yes, please turn on the video. 자, 지금 다시 제 말 잘 들리나요?
네,
네,
들립니다.
네, 잘 들립니다.
오케이. 다시 마이크로 메카닉스의 가장 기본적인 내용부터 다시 한번 진행하고자 합니다. 자, 마이크 좀 바꿔주고. 그 자, micromechanics. What can we do with these micromechanics, or micromechanical models? As we discussed together, main purpose of this micromechanics is to calculate equivalent stiffness and calculate strengths. That's two main goals. Now, additionally, we can have a simple result such as density.
화면 공유 좀.
But let's forget the others, just focusing on these one scale models. And this one can be further simplified, like just fiber, resin, fiber, resin, and so on. This can be the simplicity models, and in three-dimensional, we can have pictures like that. And here again, we have fibers. This is the fiber, and here we have another fibers, and so on. And even this one can be further simplified, something like we have only one fibers. Okay, only one fibers, so we can have this kind of a simple models. And remember, like that. And this can be always be compared with a fibers within matrix. And of course, this one, I mean, just cross sections. This one, is the simple rule of mixture. Rule of mixture. This is the scale models. And density, how can we calculate the density? Well, density, I would say, given the density of fiber and resin, there's a given, and also okay, given property, so densities of fiber and resin, and say fiber volume fraction. These are a given property, and now to calculate the density of a composite, okay, density of the composite, density to apply, same thing. So density of a composite is simply total mass of the composites and total mass of the composites. So, and if we look at the volume, of course here or there is the same thing. These are a mass of the fiber. This is a mass of a fiber, and these are a mass of the resin or matrix. We often call matrix instead of resin. So composite mass will be a sum of the fiber, a mass of the fiber, mass of a matrix, and mass of the fiber will be just a density times the volume, and the mass of a matrix will be a density times the volume, and divided by total volume. In this case, this is a simple one, simple cross sections like that. I would say the total mass will be a mass of the fiber. This is the mass of a fiber, and this young mass of the resin matrix. Of course, it's just a sum of the summation of the fiber and matrix. And by definition of this density of the fiber, the total mass will be volume times the density. Volume, we don't know how much the volume, whatever volume is, with the volume times the density will be the mass of the fiber. And same for the resin or matrix. And divided by V. And now, very importantly, this VF over V and VM divided by V, and each one multiplied by its own density. And now this one, what is called? Well, volume of the fiber divided by total volume is the volume fractions. This is the fiber volume fraction. And this one, volume of the matrix divided by total volume will be a matrix volume fractions, right? So this rho C is the one we want to calculate of the composite or unidirectional apply. Is simply multiplied by density of a fiber and volume fraction, and density of the matrix times the VM. And usually this one and VM, the summation of the each volume fraction will be 1, because the total volume will be simply each volume will, summation of each volume will be a total volume, and divided by V will be like that. So if we given the VF such as the 0.6, this will be a rho F VF plus 1 minus VF times the VM. And you can simply calculate the total density. And sometimes I'm using these simple equations. We can calculate. We like to calculate, or we like to measure the VF. We often want to measure the VF. You know, VF is the one value is very important. Oops. So sometimes we like to measure or calculate VF from a unidirectional composite, is that we can measure the a composite density, and we can measure, VF, rho F can be given, and rho M can be given. So from this equation, we can get the VF. Okay, the composite density can be measured, and fiber and resin density can be given. Then from this equation, we can get the VF. Measuring the VF is very important in composites. For example, let's say you have a little piece of the composites. Well, this can be a short fiber or long fiber, any composites, okay? Any composite, and you can measure the volume. Well, how can you measure this volume? Well, you can measure the dimensions. Of course, you can measure the dimensions and this and that. You can have a composite volume. This one, I will say again, how to measure the VF. Experimentally. To do so, again, we measure the composite volume from dimensions, or we can just pick the water and put the small piece, or some piece can be put into here, then the volume will increase. So just measure the how much volume increase, we can measure the volumes of this composite. Well, of course, we can measure the using the scale. We can measure the mass of the composites. any pieces. Can be again short fiber composite or long fiber composite. You measure the mass of that specimen, and from here we can see density of a composite will be given simply like that. And using the previous equations, I would say rho C will be a fiber VF plus 1 minus, okay, our rho and V 1 minus VF. And these are given. And fiber, density of a fiber and density of a matrix can be separately measured, right? And from these equations, so these can be given and this can be given. And so this is the how we calculate the VF. Very simple but very useful procedures. But as you can see, we need to have a precise information of the fiber density and resin density, and you need to measure the precisely mass and volume of these specimens. Okay, so this is the how do we calculate the density of composites? Now, stiffness. Well, very important procedures to calculate the stiffness. And we know that a longitudinal direction means that this fiber, as I just explained here, this is the X, usually called X directions, which indicate fiber directions. And transverse is we often call Y directions, and this is the vertical direction, is the Z. Now here is the longitudinal Young's modulus of the ply. How do we calculate? Again, the given material property will be a fiber stiffness and resin stiffness, which are given either from a manufacturer of the fiber or resin, or we can measure them separately ourselves. So given this EF and given this EM, and of course given VF, okay, VF, these are three given numbers, and how can we calculate a composite stiffness in X directions? In other words, we have a composite. This is the fiber, okay, this is the fiber, and this is the matrix and fiber and matrix. This kind of arrangement. Well, this arrangement represent, okay, this is the represent of the real composites. Very simple models. This is the, we call the simplicity model. So this is the called rule of mixture. Okay, even for density, this is the rule of mixture, very simple rule of mixture. And this procedure is called also a rule of mixture in extraction, often called ROM. And again, to define the longitudinal stiffness means that we are applying the load in extractions. Okay, we are applying the stresses in extraction. Previously, we defined as this value as sigma bar. Okay, sigma bar. is the stress we are applying in extraction, fiber directions. Now, what we like to have is the stiffness. For that purpose, we need to define the strain in extraction, epsilon x bar. Okay, that is the symbol we used to indicate the strain in fiber direction. So by definitions, the epsilon x bar equal 1 over epsilon x and sigma x bar. Of course, there can be a Poisson's ratio, but here we neglect Poisson's effect. Okay, and these are simple stress-strain relations, and these are the definition of the Young's modulus. So point is that we apply stresses, but the fiber and resin, these are all deformed together. They need to deform together, okay? Please, this is the most important observation, or this is the most important phenomena of the composites. In fiber directions, fiber, resin, they deform together. They expand together. They cannot deform like fiber this much, resin this much, and fiber this much. No way. This cannot happen. All the fiber, all the resin are deformed together in extractions. The most important observation in composites. Okay, now the force we apply, sigma bar, and multiply by total cross sections will be the force we apply, right? A times sigma x. Sigma x is again the apply macro level stresses multiplied by total, the cross sections, and which are the same as the stress in fiber multiplied by fiber cross sections, and this is the stress of the resin or matrix multiplied by the cross sections of the matrix. So simply this F is like, fiber force and fiber, the force from the resin matrix. So this is the equation we can have, and then we divide by A. And this is the simple equation we can have. AF divided by A is simply nothing but the fiber volume fractions, and AM divided by A will be volume fraction of the resin. So this is the one equation we have relating the fiber resin stress, and this is the macro level stresses. And as we just observed, the fiber strain, resin strain will be same as the fiber directional strain. We call epsilon bar, epsilon x bar. So this is the strain compatibility in extraction, and this is the basically rural mixture. So these the two observation we can have from this simple rural mixture, simple models. And for the fiber, we have a constitution, stress-strain relations. This is a material property of the fiber. This is the material property of the resin, right? Now, from this equation, from these equations, we can say sigma xf we can put these equations into here, and second equation into here, right? And as you can see here, we have a fiber directional strain and matrix strain, and which will be the same as the EX from here. I mean, this is not difficult. This one is for here, and this term goes to here. And since the strains are same, the strain will be same as the fiber, I mean the composite sigma bar and epsilon bar. Where sometimes we don't have to have a bar, but to be consistent with the previous observation, we just put the bar. But if we don't have a bar, which will simply indicate ply or macro level stresses or strain. Okay, so by definition of stiffness, these terms can be called what? This is again the relation between the stress and strain. So this is nothing but the fiber directional stiffness. I mean the composite stiffness, right? So composite stiffness will be fiber volume fraction, matrix volume fraction, multiplied by the EF and EM. So this is the simply homogenize the stiffness, homogenize the stiffness in fiber directions. And these are very close, I mean, the same as the this matrix on the density. Composite density is a simple rural mixture of the fiber density and resin density. And notice that the x-directional stiffness is just following the same rural mixture, fiber stiffness times the fiber volume fraction, and so on. Okay, so this is the procedures for homogenized. And I hope that to cover a stiffness, I mean the stress amplification factors as well. I like to get these equations. Now here is the this is a part of your homework. And stress amplification factors, well, just recalling sigma x or sigma, I would say some sigma equal at any point, can be a matrix, it can be fiber, any point will be a stress amplification factor, which is known as the M matrix. and then multiply by the sigma bar. So this one is the function of x, sigma x, and this is the sigma bar. So this is the stress amplification factors in stress. And here, let's try to have a M11 component. M11 component is that we have a certain stress like one directional, x directional, fiber directionals, and this 1 will give us the sigma. Say this is the fiber equal MF M11 times the sigma bar x, right? This is the first. This is the we have a 6 component, and among them we have a x. Now, if we have sigma bar, and this is a matrix, say we like to calculate how much stress we have in the resin in x direction, there will be a stress amplification factor like that. So I'd like to cover how to calculate the stress amplification factors in each directions. How to calculate this term, these two terms? Well, in this, I'm using the these very important equations, and from here, epsilon x can be given what? Given Vf EF times Vm EM divided by sigma x bar, and which is also same as what? Which is also same as the fiber directional strain, and fiber directional strain is given like that, and which is the EF fiber directional, X directional stiffness, and then E sigma X, right here. Simply divide by this, and these terms and that terms and all the same. So this is also same for the resin M and sigma XM. So from this, as you can see, the sigma XF will be, and multiply by EF here. You can say VF EF plus Vm and Em, and now EF times the sigma XF. Okay, so as you can see, this is the this is the terms relating stress amplification factors, and that is the analytically driven in terms of a fiber property, resin property, and fiber volume fractions. Well, you can easily get the same result for this. So these are terms for here. Okay, this is the term and this is the a term. So following the same procedure, we can get all the stress amplification factors. As you can see, by definition of this stress amplification factor, if you know how much stress you apply in fiber direction, you can immediately calculate you can immediately calculate how much stress is in the fiber. Same for the resin. Same for the resin means that we don't have to drive, but we can have a sigma m x equal and the em and vf ef plus vm and em times sigma x. Okay, sorry, this is not the this is the sigma x bar, right? Sorry, and again this is sigma x bar. So this will corresponding to this will correspond to this guy. Well, okay. So I hope this can be understood well, and I hope that this derivation will help you better understand the stress amplification factors. Again, once you have this stress amplification factor, you can easily calculate the local stresses. And then main purpose of this stress amplification factor is that, let's say you have a resin strength, okay, resin strength, then strengths you can compare and you can calculate whether this resin will fail or resin will go into a plastic zone or plastic behavior, because this is the stress we're gonna have in the resin for the given on-axis stresses. Again, it's so important results. Even though we followed simple procedures, but physically it has a physical meaning in there. Okay, now let's move to different directions. Different direction means say we this is the again simple rural mixture models, and we are applying the load in transverse direction here like that, and then again, we like to calculate the equivalent or homogenized stiffness of a composite in y directions and in terms of fiber and resin properties, and also stress amplification factor as well. Well, as you can see, stress amplification. Okay, let's drive. And here, of course, we assume 1D behavior, one-dimensional behavior. Of course, we can consider the Poisson's effect, but just follow the simple procedures. Now, again, the force we are applying is in transverse directions, and fiber and resin. This is the resin and fiber, and resin and fiber, and so on. They are connected in series like that. And the deformation we have, actually, under this one, deformation we have, say this is the delta y. This is the deformation. Okay, this is the deformation of composite, and well, unfortunately we don't have that equations, but delta y is the composites will be simply delta fiber plus delta m. Delta means the deformations. Deformation due to in the fiber and deformation in the matrix. And this delta is what? Delta fiber direction delta will be simply a length of the fiber times the strain. In this case is the y directions. And the length of the resin and y directional strain of the resin. So this will expand. This one, for example, will expand, right? Somewhat expand. This is the fiber, and this one length is given as the fiber directional, the fiber length, and the strain of the y directional strain is the simply delta divided by LF. Same for the resin. So that's why we got this equation. And then this delta y, by definition, we can define as the total length multiplied by the fiber directional and the transverse strain. And then we divide by the L, divide by L, divide by L. That's why we got these fiber volume fractions, right? LF divided by L will be a fiber directional volume, fiber volume fraction, and LM divided by L will be a matrix volume fractions. And then we have this. So this equation looks like a rule of mixtures in y direction. Again, y directional strain is following the rule of mixture. And now in the force distribution, since we are applying the sigma y bar, and by equilibrium, this stress will be the same as the in the fiber, same as in resin system. So simply the fiber the stress we apply will be the same as in the resin, and the same as in the composites. So these are two observations we can have. And now by definitions of this sigma bar and epsilon bar, and we have these terms. Again, this sigma, we don't have this equation, but we have it here, right? We have this, and this EF will be these terms, sigma F, EF will be here, and this strain will be here, right? And then we use these conditions, and we have a common variable, sigma y bar, right? So now by definition of the stiffness of the composite, this is the what? This is the 1 over EY. So 1 over EY is given as the fiber volume fraction divided by EF, and matrix volume fraction and EM. So this is the rule of mixtures to calculate the EY. Now, how to calculate the stress amplification factors? Well, simply, as you can see, this is the stress amplification factors. When we apply the sigma y1 and back to here, this sigma bar, second term, I would say this is the sigma x bar and sigma y bar, and this M22, okay, M22 will corresponding to the term relating the sigma 1, sigma y bar, and sigma y. So M22, so this is, look at that, y and y. So M22 will be simply 1 fiber, and M22 matrix will be simply 1. And well, how about the other terms? You may ask, how about this, M21 and M12? Since we are considering the one-dimensional, well, we don't consider Poisson's effect, you can assume the 1, 2 and M1, 2, 1 equals 0. So only diagonal term will exist in these derivations. Okay, and then we can do the same thing for the shear modulus. Shear is like that, and again we have fiber lengths and matrix lengths and so on. And we apply sigma s, which will be a macro level stresses. And each one, this fiber will have a certain shear strain, and resin will subject to another shear strain like that. And then stress we are applying to here, the stress applying to fiber and stress applied to resin, and there will be all same because similar to a equilibrium, they are all same. Here, same ratio applied to here. When we apply the spar, this is stress fiber, stress resin will be the same. This and that will be the same, that one. So the stress will be the same. Now, how about strain? The applied strain will be under the load. This can form some like on the number, and so this will be a and the shear strain. So this strain will be follow through because the amount of this angle and that angle and that angle